legacy. So let's watch Taylor series and its application in differential calculus. So here I have taken y equal to fx, and at the neighborhood point of x or x plus h, where h greater than 0, we wish to know what will be the function at the neighborhood point of x plus at the neighborhood point of x or at the point x plus h. So it is by Taylor series expansion, it will be fx plus h first derivative of x plus h square by 2 factorial f second derivative of x, and in this way up to infinity. So this is the Taylor series. We can write down in sigma structure in this way. This is fn x n is equal to 0 to infinity, and here this is h by 0 factorial n factorial. In better terms, this can be written down h summation sigma into 0 to infinity f nth derivative of fx by n factorial. So in this way we can express Taylor series. Now what is the importance of Taylor series in different? This is raised to the power n also. So now its importance in differential calculus is that we can calculate many differentiation. We can find out many limiting values through Taylor series in very easy way. Like if we have a function fx is equal to sin x by x, then and if we wish to know its limiting value, then we have to just express sin x in terms of Taylor series in this way. So this series can be written down in this way also. Fx is equal to f0 plus x first derivative of x at the point 0 plus x square by 2 factorial second derivative of x at the point 0 plus dot dot up to infinity. So here we have to express sin x in the derivative forms. So here fx is equal to, we are taking gx is equal to sin x. Sin x is taken gx. So now first derivative of gx will be cos x. Second derivative of gx will be minus sin x. In this way, third derivative of gx will be minus cos x, and so on up to infinity. And here if we put 0, then g0 will be sin 0, the value is 0. First derivative of the x at the point 0 will be cos 0, its value is 1. Second derivative of gx at the point 0 equal to minus sin 0, which will be 0. Third derivative of gx at the point 0 will be minus cos 0, this will be minus 1. So in this way we can expand this series. Now if we put these values, taking gx as a sin x, then gx will be g0 plus ax g, first derivative of gx at the point 0 plus x square by 2 factorial, second derivative of gx at the point 0, and in this way so on up to infinity. Now g0 is equal to 0 plus x, first derivative of gx at the point 0 is 1, so this will be x, plus second derivative of gx at the point 0 is 0, this will be 0 again. Then third derivative of gx at the point 0 is minus 1, so this will be minus x cubed by 3 factorial plus, so dot dot up to infinity. So now we have the series x minus x cubed by 3 factorial plus x5 by 5 factorial minus x7 by 7 factorial, and so on. So in this way we can expand gx or sin x, sin x. Now if we replace these values in this function fx, then we will get so fx, which is sin x by x. Sin x I have taken, we have got x minus x cubed by 3 factorial plus x5 by 5 factorial minus x7 by 7 factorial plus dot dot up to infinity by x. So x not equal to 0, since x is the denominator, so we can just take common, or we can divide the numerator by the denominator, and we will have 1 minus x square by 3 factorial plus x4 by 5 factorial minus x6 by 7 factorial plus dot dot up to infinity. Now if we take the limit now, where x tends to 0, sin x by x, then at the limiting point at 0, all these terms will be 0 other than 1. So this function fx limiting value at the point 0 will be 1. So this is our first limit. First limiting value of a limit function of a function. In this way, if we take limit x tends to 0, 10x by x, this will be again equal to 1. So what will be exponent e to the power x? If we take gx is equal to e to the power x, then e to the power x will be, if we again recall the series, gx is equal to g0 plus each g first derivative at the of gx at the point 0 plus each square by 2 factorial second derivative of gx at the point 0 plus up to infinity. Now if we put these values, e to the power x will be e to the power 0 is equal to 1 plus, this will be actually h, not x, this will be also x. So x, first derivative of gx will be e to the power x again, and if we put g at the point 0, we put 0, x is equal to 0, then it will be 1. So x multiply 1 plus x square by 2 factorial. Here again, if we put second derivative, the second derivative of gx will be e to the power x again, and at the point x is equal to 0, it will be again 1. So this will be 1 plus. So in this way, the series expands. Now, you can write down e to the power x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial plus dot dot up to infinity. Now if we rearrange this, it will be e to the power x minus 1 is equal to, now we take a common x from the remaining series. So this will be x under bracket 1 plus x by 2 factorial plus x square by 3 factorial plus dot dot up to infinity. Now again, if we rearrange this, it will be e to the power x minus 1 by x is equal to 1 plus x by 2 factorial plus x square by 3 factorial plus dot dot up to infinity. Now on this function, if we take the limit where x tends to 0 to the power x minus 1 by x, then we can look that at the limit point where x tends to 0, all these values will be equal to 0 other than 1. So this function's limiting value at the point 0 is 1. So these are the very important formulas also to solve many problems related with the differential calculus. In this way, we can prove other trigonometric functions also, like limit x tends to 0 log of 1 plus x by x is equal to 1. So this type of formulas are required to solve many limit related problems. So we need to study very deeply to solve such kind of problems. So thanks for watching. If you have any question, then comment me.